Let's begin. So some of these are relatively easy, some of them are a little bit more challenging. A book is at rest on a tabletop, diagram the forces acting on the book. So you've got this, and you've got that, and you have to label them. So that's our weight force, and that is our normal force. And I'm going to guess that everybody got that. I'm hoping. Do you need to draw? Do you need to draw this?
No.
Yeah. Yeah. Is that your question?
Yes, and also, do you have to gravitational force if it's not falling or anything?
Yes, you do.
So would that be the same as weight force?
Yes, weight force and gravitational force are the same thing. Okay, Connor, you need to pay attention now. We've begun. All right. Number 2 says, a girl is suspended motionless from a bar which hangs from the ceiling by 2 ropes. Diagram the forces acting on the girl. So once again, is there going to be any of these without a weight force or gravitational force?
No.
Okay. There's 2 ropes, so you probably should have 2 smaller arrows that are labeled like a tension force or something like that.
You just have one going.
Okay. You could have one. It's kind of important when we get to grade 12 because I might ask how much tension is in each one of the ropes. So for example here, yesterday, remember, if this is me hanging from here, remember I weighed 750 newtons, wasn't it?
Yeah.
Okay. So how much would each of these tensions be worth? Would they be each 750?
No, they'd be 325.
They'd each be
325.
325, exactly. So in that sense, Matthew, it is important.
No, it wouldn't be 325. You're saying
375, right?
Yeah.
In that sense there, it is important that you have 2 because each one only has half the force, half the tension. So, in the long and short is yes. Yes. An egg is free falling from a nest in a tree. Neglect air resistance. Diagram the forces acting on the egg as it falls. Is there anything else?
No.
No, there is not. Why not? It's just falling, right? It's not sitting on a surface. In fact, is this one accelerating?
Yeah.
There's a net force. It's accelerating. It's changing its speed. A flying squirrel is gliding, no wing flaps, from a tree to the ground at constant velocity. Consider air resistance. Diagram the forces. Obviously, weight force. Because it's at a constant velocity, this means that my net force is 0, which of course means my acceleration is 0. The forces must be balanced, and so I've got, now this would not be a normal force gauge because it's not on a surface. This is a friction force, air resistance, something like that, right? It might, yeah, it might.
Why is the friction force on top of the house? It wouldn't there be one at the side?
Could be, yeah. Do you want to maybe put it, if you think that it's, do you want to maybe put it like this? Okay. That's okay.
I just changed it.
It's okay. A rightward force is applied to a book in order to move it across a desk with a rightward acceleration. Consider frictional forces, neglect air resistance, diagram the forces acting on the book. Weight force. Is the normal force balanced? It is, but it's moving to the right with a rightward acceleration, and there is friction. So you put the friction over here, and my applied force is going to be?
Much bigger.
Much bigger. Much bigger. Yes, good. Now, number 6 is exactly the same. The only difference here is that it's not accelerating. It's in fact doing what?
Constant velocity.
Constant velocity. So what does that mean?
Friction and net force are applied
Yeah.
to the same.
Friction and the applied force are the same. I'm not going to get my ruler out as long as they're reasonably close. Yeah? Good?
Yeah.
Number 7, a college student rests a backpack on his shoulder. The pack is suspended motionless by one strap from one shoulder. Diagram the vertical forces acting on the backpack. So we've got gravity, Is it accelerating up and down?
No.
No, so therefore it must be balanced. Then it's a rope or a strap or something other, so it's tension.
Rope
So
knot.
if it had both straps, would it be like?
There would be two of them, yeah. A skydiver is descending with constant velocity. Consider air resistance. Is this not the same as, no, the egg was, right?
No, consider.
Yes, so this time now
No, it should
be a friction force, right?
Well, it says constant
Should
velocity.
be a little less.
Should be constant velocity, so it should
Constant velocity, so they have to be the same. Now, do you think that's what I'm looking for when I give you constant velocity? Like, do you think there's a mark for making them equal?
be. Yes.
Absolutely there is. So make sure of that.
If you don't think if it's accelerating or constant, do we assume? Like,
You would have to, I assume this, and then I would mark it accordingly. Okay, loosely packed snow. I think I told you yesterday that loosely packed snow is code for
Some friction.
some friction, exactly. And it has a rightward acceleration, weight force, normal force, some friction, applied force. Are you finding these relatively easy to do?
Mm-hmm.
Yeah, not bad? Great?
When you're drawing that acceleration, does it have to be like significantly bigger, like you have it, or can it just be like?
Significantly enough that when I don't have to get a ruler to check to see if it's big or not, right? And it's the applied force, not the acceleration. Okay, now what about number 10? How many people have something that looks like that? Just both? Few?
Football. I got 2 arrows going down and 1 arrow going back.
there's
We're not
one arrow
supposed to use
going
it.
to the
That's too bad because that's what the answer is.
Yeah, but.
Is this any different? I always get arguments over this one. Is this any different than the egg free falling?
No.
No. Do I need to show the motion of the football?
No.
No. The arrows do not show motion. The arrows show forces. Forces. I'm going to throw the ball at Ben. See if Ben can catch, right? Pretend it's the football. When the ball is like, right about there, if I threw it over here, right over Casey's head, am I applying, I'm not going to hit you. Am I applying the force to it right now?
No.
Not unless I'm a Jedi Master, which I am not. I wish I was, right? When do I apply the force?
Beginning.
When I've got it in my hand, right? Or when it's the football's on my shoe, right? But it clearly says, after having been booted, an object in motion will stay in motion. I do not need an arrow showing it going that way. The arrows do not show motion. The arrows show forces. There is no force other than gravity acting on it. You could argue if you want. I will accept this. You could say, Mr. Bennett, there's some air resistance. Okay, but it would be there. Bingo.
So it's wrong.
Okay? Do you think that is an important question?
Yes.
Do you think I will ask it exactly that way? No.
Yes.
No.
Please do.
I won't. Okay? I am asking a question. Do you understand that an object in motion stays in motion and you don't need a force to keep it moving?
Uh-huh.
That's what I'm asking.
Uh-huh.
Okay? Number 10. A car is coasting to the right and slowing down.
Which means the friction's greater than the acceleration.
I drew an actual car.
Is that what it looks like?
No.
That's what I did.
Why not?
The friction should be greater than the acceleration.
It's not an acceleration, it's a force. The arrows are only forces.
Applied force.
There is no applied force.
Oh, because it's already moving.
A car is coasting to the right. That means no applied force.
Oh.
No applied force. You do not need to show that it's moving. You can deduce, you can figure out that it's moving because if there's friction, right, and there's no applied force, then it has to be moving and slowing down. What happens when it stops? Does the friction force keep on pushing?
Yeah,
It's still there, but
Okay, if the friction force continued to push, then this is what would happen. It'll go the other way. The ball will stop, and then the ball will have to come back, right? Because the friction's still pushing. The ball coming back?
no.
So what happens to friction?
It does- disappears.
It disappears. Disappears.
If the vehicle's still in gear, there's still a force.
You're right, yes, I know. There's always some power mech guy that says,
That's
yeah.
what I was thinking.
Okay.
I didn't even get it wrong.
All right.
That's not cool.
Right in there, I assume that. So, what we're going to do here today is we're going to do some sample problems. Your eyes are going to go like this when you see some of the answers, because they're fairly long, and yes, I expect you to do them, and yes, they'll be on the test. Okay? So I strongly urge you in the strongest manner possible to make sure you copy down these examples, and I want you to understand that it's not the answer, it's the process that matters, okay? Take your time and let's Mike Holmes it and do it right. Okay, I have two formulas there. We're going to use them both. A constant force acts on a 12 kilogram mass. My mass is 12. It changed its velocity from 4 to 8 in 3.5 seconds. What is the force? My time is 3.5. My 4 and my 18 are both velocities. What are the names given to the 4 and the 18?
Forces.
They're velocities.
Oh.
Initial and final, exactly. The initial is 4, the final is 18, right?
What's that top line at 12?
Mass is 12. Okay, we need to know what is the force. My last thing down here is going to be F equals something. Right? That's the last thing. It's going to be down in the bottom right-hand corner. Okay? So let's figure out the route we have to take. Let's start from where we want to be. We need, at the end, we're going to use F net is equal to MA. That's the last formula we're going to use. So how do I get there? I have the mass, but I do not have the...
sorry.
So I got to find acceleration. What's the formula for acceleration?
Change of view.
Delta V over delta T. Do I have the T? Do I have the delta V?
Yeah.
Not quite yet. So back up one more. Delta V is equal to VF minus VI. Do I have the VF and the VI? I now have my root. Notice how I started on the right and I work to the left, because when I read it eventually, I'm going to have to go
Other way.
the other way. That's a nice little skill, a nice little sort of process to use. Okay? Now eventually, obviously, you're going to be able to look at a question like this and go, oh, I know what I need to do, and you're just going to start there, and you're going to go left to right. But if you have to, do that sort of backwards to frontwards rotation kind of thing. Okay, so delta V is equal to 18 minus 4, which of course is not 12. And now I'm going to take that 14, and where is it going to go?
On top.
It's going to go right in there, right? For delta V, exactly. So A is equal to 14 over my time, which is 3.5. 14 divided by 3.5. 3.5 times 2 is 7, so that's going to give me 4. And now that 4 there is going to go in for A over here. And I get a net force.
12 times 4.
12 times 4. My F net is 48 what? Newtons.
So what did I ask for?
The net force. Yeah, they're asking for, well, not exactly all the time. Is there any friction involved here? So what I'm really being asked is, what is the applied force But because there's no friction, the applied force is equal to the net force.
Is the F for newtons always capital?
There's some controversy there, Ben. The latest stuff that I'm reading says that it's a small n, that you abbreviate with a small letter, although traditionally it's always been a big N. So there's a bit of, I'm not going to worry about it, but in some books you see little n, which kind of looks weird, but
Is that in physics monthly?
I don't know. I don't subscribe. Yeah.
So as long as there's a ring, you're gonna mark.
Oh yeah, I'm not going to worry about big or small.
Alright.
So when you write it, usually it's kilogram meters per second squared, kilogram meters per second.
Yep. Kilogram meters per second squared. Exactly. Okay. So how many marks would that be worth?
Four.
Likely 3.
7.
1, 2, 3. In that order, please. Answer in the bottom right-hand corner.
Well, 4. Do you want us to circle that answer?
No, but I don't. You can put circle or box or whatever. And, you know, I look in the bottom right-hand corner of your solution space. Okay. Don't have your stuff all kind of crazy all over the place.
What if we lost it?
Boxes is good. Yeah. Okay. I'm not going to be an ogre about, you know, those kind of details, but at the very least, put it in the correct order. Okay. Now, example number 2. There's one significant difference about this. Let's go back. I didn't draw a picture here, did I?
No.
Let's draw a picture here. If I'd asked for a picture, I might have given you a mark for that. Okay? The picture is going to look like this, isn't it, right? I got a 12 kilogram mass, and I have an applied force. What's different about this scenario
Doesn't have a velocity.
from this one?
Doesn't have a velocity.
There's directions.
Okay, this one is sort of one-dimensional, right? Left and right, no friction. You're right. This one has friction. It's two-dimensional. It's south and east. So instead of me looking at it sort of like sideways from the side, I'm looking at this one
Yeah.
like bird's eye view, right? Top down kind of thing. So what would this picture look like?
Well,
I'm going to ask you to draw the picture while I go do my attendance. You should actually have 3 forces. Force 1, force 2, and friction. Let me draw. Friction. Sure. We've got F1, which is our 250 south, and my F2, which is 150 east, which means what direction is this thing going to go?
that way.
Exactly southeast or more south than east?
South.
More south than east, right? So kind of like this. You don't need to draw that one on there. If I were to draw it as a vector diagram, tip to tail, well then, it would be like that, wouldn't it?
We don't remember that.
You're going to have to. Because we're going to be using it right away. Okay? So, in fact, if it's going that way, which way is the friction?
The opposite way.
The opposite way, which would be like, kind of like,
That's kind of just like,
well, that, right? So, in actuality, your vector diagram gauge is going to look like this. If I draw my vector diagram, it's going to look like this. There's force 1, there's force 2. Where do I put the blue one for friction?
Right there.
Tip to tail. And so my overall net force is going to be? Like that, right?
Yeah.
I'll draw it bigger. Yeah, I'm serious. Down, to the right, friction. There's my net force.
you want to draw
You can. How am I going to find this out? You're going to have to do it in steps. Okay? Now, can I just go 250? Let me get rid of some of that. Can I just go 250 plus 150? Well, that's 400. Minus 50, that's 350. Can I do that?
Sure.
I could, but only if I want to do it wrong.
Oh.
Why can't I do that? Because the 250 and the 150, I have to add the direction as well, just like we did way back when we add vectors. We have to add those vectors properly. So step number 1 is to really figure out what this force is, and then we're going to subtract our friction. So I'm going to call this one F1 and F2. I'm going to call this one FA. Is that okay? Like the combined applied force of F1 and F2. Is that okay?
Sure.
Sure, that's okay. So I'm going to write FA squared is equal to F1 squared plus 2 squared. How come I can do it with Pythagoras?
Because it's the right triangle.
Because it's a right triangle. If it was not a right triangle, Matthew, I would have to
I don't know.
break out the rulers and protractors.
Oh, right.
FA squared is equal to, how much is my F1?
250.
250 squared plus F2, 150 squared. Good?
Mm-hmm.
Can all of you just go straight to an answer here, or do I need to show intermediate steps?
Go straight to it.
I can go straight to an answer? Okay, so it's just going to be like 250 squared plus 150 squared. Find the answer, take the square root.
Which is what?
I'm going to look it up. Did you get 291.5? Okay. So, in a sense, my total applied force is 291.5. The object doesn't care that it's 250 and 150. It just knows it's got 291.5 newtons of force being pushed on it.
Mm-hmm.
Okay? Connor?
Find the acceleration, then we need a time.
We'll see. We'll get there. That reminds me of a little comment I have to make, so hold that thought. My 291.5 is my applied force. Now I'm going to write net force is applied force. What was that formula at the start there?
FA.
Okay, hold on here. I got FA plus FF.
Wrong.
Not exactly. F net means sum of all forces, and sum means add them together. But the friction force, Ben, is always
Negative.
opposite the motion, which makes it
Negative.
negative. So I'm really subtracting, but I would prefer that you show it as adding a negative, because that's really what it is. Okay? So I'm going to write FA plus FF, and so now I get 291.5. Can I just write minus 50 there? Is that okay? Giving me a net force of 241.5 newtons. Yeah? The friction, minus 50, right? Now that I've got my net force, I can write F net is equal to MA. And now my net force is 241.5. My mass is 100. Solve for A by dividing by 100. 2.4 meters per second squared. And that's the end, right?
Mm-hmm.
Okay. Connor's question was, did we need the time? And no, we don't, right? Not to get to acceleration. If we want to go any further, then we're going to need time, okay? Now,
Let's say,
Is that meters
let's
per
say
second squared?
that somehow in the example they put in, let's say kilometers per hour, then you have to convert it
I
out.
guessed, yeah. I like to call this formula the bridging.
Verging.
Yeah, the bridging. B-R-I-D-G-I, bridging. Let's see if it recognizes it. Bridging. It's the bridging formula. It's because it bridges from dynamics, which is all the force stuff that we've just done, and it takes us to
Kinematics.
kinematics, which allows us to do how far does it go, how long does it take, how fast is it going, all that stuff. All the stuff that we just spent the last 3 or 4 weeks on. Okay? The only way to get to all that stuff is through F net is equal to MA. It bridges dynamics to kinematics. You have to get there. Okay? So use that as sort of a halfway goal a lot of times. Okay? This question didn't ask for it. The next one does. Okay? The next one does. Are we good? I'd like you to read this and draw the picture. Does it matter that the kid weighs 50 kilograms and the sled is 15?
Yeah.
You've got to add them together. I would likely give you a freebie mark for Add them together. Don't lose out on that 3D mark. 65. It's a frictionless ice surface. That's good. Does the weight force and the normal force matter?
No.
Weight does.
Probably it doesn't matter. Quite a few textbooks or whatever would probably show it even though it doesn't matter. It just confuses things, right? But to be complete, you should really draw them in there. I personally am not going to worry about it in this case. Now, what does it mean that the rope makes a 30-degree angle with the horizontal? What does that mean? It's up at an angle, right? In fact, it's a 30-degree angle. Now, this opens up a whole new concept known as components. And they are very important when it comes to grade 12. And certainly in this little spot right here, it's important. So I'm going to label this one F, or FA if you wish. Right? It's the applied force. Does all of that 250 newtons go into pulling it sideways?
No.
Pulling it up too.
Lifting it up as well. Okay. So Matt, if I increase that 30 degrees to say 60, would there be more or less pulling it sideways?
Less.
Less, right? So it matters. Okay. I need a name for that pulling it sideways force. We call this the horizontal component, FH. FH is the horizontal component. It's how much is actually pulling it sideways. Now, if you look at that diagram on the board there, it has nothing to do with you guys, it's grade 12, projectile motion. When it's moving in 2 dimensions, there's horizontal and vertical components. Okay, we'll get to that. Okay, but this horizontal component deals with that as well, grade 12. Okay, so how do I find this horizontal component? Well, fortunately, first of all, too, there's a vertical component, and they will always be at what angle to each other, the horizontal and vertical? 90 degrees. So that means we instantly have created a what kind of triangle?
Right.
Right triangle, which means we can use Pythagorean and sine, cos, and tan. And there's much rejoicing because, oh, I haven't used that button on my calculator for a long time and I've really been missing it. No? Not so much? The angles do, but I need to know what this side here is. Okay? So this side is the adjacent, right? Let me just redraw that triangle a little bit bigger for you. Adjacent, opposite, right? Hypotenuse. I hope I've given you lots of room here. Yeah, I did. Did I? Okay, good. This is my angle here. The FH is the adjacent. So I'm going to write cosine of 30 is equal to, should I write adjacent over hypotenuse? Yeah? Adjacent over hypotenuse. And my adjacent side is my horizontal component. And my hypotenuse is my applied force, right? My F, my applied force. I can rearrange that to solve for, oh, do I have that applied force? I do, right? Yeah, I wrote way too much here. Applied force is 250. How do I solve for FH? Multiply by 250, right?
Goes 30 and then you get a decimal and you just times the
250 times the cosine of 30, which should give you some number that's bigger or smaller than 250.
No, smaller.
Smaller.
I have my scientific calculator here. You can use mine.
You're going to need your scientific calculator. So it's 250 cos 30 or 216.5. Yeah, well, you'll have to figure that out. We'll get, don't worry, we'll get to that. Okay, now, Mr. Bennett, that's a lot of work. Do I have to do that every time?
Yeah.
No. Can I come up with a rule for FH?
Not enough.
Is the FH always going to be the adjacent one? Because that's always going to be the angle. It's never going to be this one up here. It's always going to be what's the angle it makes with the horizontal. Always. So it's always going to be adjacent. So could I not just say, could I not just take this,
Just say FH times.
could I not just take my FH up there? Or sorry, yeah. No, that's not. This is not FH. This is FA. Could I not just take that up there? And are you telling me that the FH is always going to be F cos theta?
So you're always gonna pass the force times the angle?
Yeah.
That's smart.
FH is always going to be F cos theta. Always.
How come you didn't just tell us that?
I want you to see where it comes from. If I just told you that, you'd go, I don't know where it comes from. That is a formula that you can use.
Does F represent that, right?
Yes.
Is it always gonna be that, right?
Yes.
FH?
Unless, Gray, in the very rare occasion when there might be two forces or something rather, but then you'd have to do two horizontals and add it together and that.
I guess it's like 2 rows or something.
Yeah, different angles, yeah. That's an extreme situation. Okay, so FA is going to be that. All right, so now I've got my horizontal force. Now, we are lucky in that there is no friction here, right? If there was friction, I'd have to subtract it to get my net force, right? But there isn't. So in this case here, do you guys know what 3 dots in a triangle means? Means therefore, yeah. 3 dots in a triangle means therefore. Okay, so therefore, my net force is equal to 216.5.
Is that also new?
Okay?
3 dots?
That is 3 dots what?
Is the 3 dots like a Greek?
No, I don't know what that is. It's not a Greek letter. But
Do we need to do the 3 dots?
Yeah.
If we didn't, we'd lose markers.
Okay, so now that I've got my net force, now what do I have to actually solve for? I'm trying to find the final velocity and the distance. Those are kinematics. To get from forces to there, I'm going to have to go through F net is equal to MA. Oh, let's get rid of this stuff.
Oh my goodness.
Are you starting to see that showing your work's going to be important? I really hope so. You're going to be lost if you don't show your work.
I'm lost.
I'm hungry.
F net is equal to MA. What's my net force? 216.5. What's my mass?
100 kilometers, or 65.
Okay, so how should I be writing
65.
this?
Well, I'm sort of going left to right and top to bottom, right? Sort of.
Oh, but mine looks like this.
Yeah. Well,
Do I put this down under this?
sure. Yeah. Yeah. Now I have to find my acceleration. 216.5. Same as this number, right? Right? Same as this number, F net. So yeah, there's lots more. What's my acceleration then? It's going to be 3.33.
He's starting from stop, right?
Yes, if it doesn't say, you can assume it's from rest.
You want to start with that? Because I know you know the answer.
Eh?
You move on. Do you want to round it up?
Leave it at 3.33.
Then when you get to 9.9.
Divide by 65, right?
Oh, no.
Yeah, divide both sides by 65.
When you get to 9.99.
Yeah, I'm going to round that. All right, now I need to get to final velocity. How do I get to final velocity from A? Right?
It's 3 seconds.
Delta V is equal to 9.99 meters per second. The velocity changes by 9.99. Is that the final velocity? It is. Can I just say, therefore, the final velocity is, we're going to round this here. Can I do that?
Yeah.
Yeah.
I think we're all big enough, boys and girls, that we know now that if the initial velocity is 0, that's the same as my final velocity. I'm hoping. Okay? What if it isn't? Then you do delta V equals VF minus VI, and you find out what the final velocity is, right? But a lot of the time, it's 0, right? Like 90% of the time, it's going to be 0. Most of the time, the initial velocity is 0 channel. So if it starts at 0 and it changes by 10, then what does it end up at? 10. If you got no money in your pocket and I increase that amount by $10, how much have you got? $10. But if you got 5 already, how much have you got now? 15. Okay. So I've solved for final velocity. I need to solve for distance traveled. The only way to get to distance is through average. Right? And once you got the average, then you can get the distance. How many marks do you think this whole giant thing is worth? 1, 2, 3, 4, 5.
Will you scroll down again? Will you scroll down again?
Okay, maybe 6 to 65. Sure.
Scroll down again? Thanks.
Yes. Okay? Again, that is the sort of the biggest that you will see. Like, right? That's the degree of difficulty. Do you now see, I also picked this one because do you see how it matters about writing the formula?
Yeah.
Like, if you just had numbers, like, completely and utterly chaos, not good. I need the process. Okay. You're not going to fail it. You're going to practice and you're going to get good at it. We've just begun. We've just begun.
But we're having a test like next week, you said.
Today's Tuesday. It's like a whole week and a half away.
There's no school Friday, and I'm not here Thursday, so tomorrow's my last day.
You'll be fine. I would like you to try example number 4 on your own. Draw a line down the middle. I will tell you this. It is a 2-step question. 2 marks, 2 formulas. Draw a line down the middle. Put the... Yeah, I'll tell you how many marks it is. It's usually a pretty good indication. Okay, let's have a quick look at this here. What do we know? We know that the mass is 1,800. We know that the acceleration is 1.75. I know that the friction force is 250. And I have to solve for the applied force, right? So, with my M and my A, I can get myself F net is equal to MA. I can go 1,800 times 1.75 and get 3,150. Oh, this is easy, right?
Yeah. It's easy, but
Yeah, I just take 3,150, subtract 250, and get 2,900, right?
Well, why didn't you subtract it?
Because you're
I know, but like,
How many people have that answer?
Yeah.
because
Get out your erasers.
you switch to 250.
I knew it. I knew
Very
it.
good, Matthew.
Oh,
The mistake that I made, and I did it on purpose, the mistake that I made was I didn't write the formula. I did it to show you what happens when you take shortcuts and you don't write the formula. Watch. Says Mr. Bennett in his smug voice. F net is equal to the applied force plus the friction force, right? What is my F net? Write it in right below it, like I've shown you. The net force is the applied force plus the friction force. My 3,150 is my net force. I'm solving for the
FA.
FA. What is my friction, Matthew?
Negative 250.
Minus 250. And when I take that to the other side,
Counts in half.
it becomes a positive, and it is not stupid. The applied force is 3,150 plus 250, which is 3,400 newtons.
Ouch.
The reason you made that mistake was because you didn't write the formula.
I wrote the formula and everything.
Now think about this for a second. Why is the applied force more than the net force? You need 250 newtons just to overcome friction, and then you need another 3150 to do the acceleration. So I need a total of 3400. The net force is always less than the applied force when there is friction. Okay? I threw that curveball at you for a reason. Okay?
What was the curveball?
Yeah.